So Eg and T2G, these are the two splitted energy levels of the octahedral complex or metal atom of octahedral complex. For D1, D2 and D3, there is no problem in the filling of electrons as they all will go to T2G level only. But for the D4, fourth electron either has to occupy T2G level or Eg level. So in which side the electron will go, it depends on two factors known as pairing energy and octahedral splitting. This is a octahedral energy or octahedral field in strength. The higher the gap, larger will be octahedral energy. Now in case this octahedral energy or splitting energy is less than pairing energy, it means pairing requires more energy than octahedral. The electron will try having a priority to occupy upper energy level, go to Eg level, T2G. So 3 electrons will be in this one, T2G, and 1 will be in Eg level. That's what we'll get. This is the complex we'll get. T2G 3, Eg1, 4 unpaired electrons. This happens only when octahedral field is small compared to pairing energy, and octahedral strength will be weak only in case of weak field ligands, like we just saw in this our spectrochemical series. The weak field ligand like chloride, bromide, iodide or thiocyanide, they will give us high spin complexes having a higher number of unpaired electrons. So weak field ligands will give us low octahedral splitting, and that gives us a high spin complexes. Cobalt hexafluoride, water complex, aqua complex with cobalt are examples of weak field complexes. Now next is when this octahedral splitting is greater than pairing energy. So what happens? Electron will try to occupy the lower orbitals only through pairing. So we're getting a T2G E4 and Eg0, mean all 4 electrons will be in the lower d orbitals. Pairing will happen. These are examples of low spin complexes or strong field complexes, like ammonia and cyanide with same cobalt metal atom gives us a low spin complexes. Why? Because ammonia and cyanide are, as you know, strong field ligands. Transition of electrons from T2G to Eg will result in color of compounds. Larger the crystal field splitting, bigger will be the energy gap. More energy will be required for transition of electrons from T2G to Eg. So, high energy, high frequency or lower wavelength will be absorbed, and correspondingly complementary higher wavelength will be emitted. And with energy splitting, it goes to higher energy state. Here are certain examples of colored complexes. Here we are having a pentamine chloro cobalt complex. Cobalt is we are having a 3+ oxidation state, and it absorbs 535 nanometer, which is yellowish, and to us the color will be we observe complementary color, which is almost looking like a violet. Here again, we having all strong field ligands. Here, so you see, lower energy is absorbed because field strength is higher. One water molecule is a strong ligand compared to chloride. So lower wavelength will be absorbed, which is a bluish greenish, and color will start appearing reddish. In titanium complex with water we know is a relatively strong field ligand compared to chloride. So what happens? Energy absorbed is 498 nanometer. Again, cobalt complex, hexamine complex, its energy will be still lower, which is bluish region. Color absorbed will be yellow orangish. And with cobalt cyanide complex, cyanide we know is the strongest ligand among all these, even stronger than ammonia. And we having a 3 negative is an anionic complex. Energy absorbed is a 310 nanometer, which lies in ultraviolet region. And color is pale yellowish, very pale color we observe. So observed color will be complementary to the absorbed color. And wavelength will increase, wavelength will reduce as the ligands bound to the metal atom of the same charge are strong field ligands. Now we will talk about tetrahedral complexes. In tetrahedral coordination entity, we are having 4 ligands. So here we take example of a zinc atom surrounded by the 4 ligands. 4 ligands will approach the metal and binds to it. So binds to the metal atom. We are having this is just for our. Now here you see the ligand do not approach directly along the axes but in planes only. So opposite to the octahedral complexes in which ligands directly approach the axes, in tetrahedral complexes ligands approach along the inter-axis points. So the orbitals which are lying in between the axes will experience greater repulsive force compared to the ligands lying directly along the axes, like our dz square and dx square y square orbitals will experience lower repulsion compared to dx, dy and dz. They will be feeling more repulsive force. So splitting for tetrahedral complexing will be opposite to the octahedral complexes. What happens here? dx, dyz and dxz will go up higher in energy. dx square, y square and dz square will go lower in energy. That's what we'll get. They will experience same like octahedral complexes. They experience repulsive force with the approach of ligands, and their energy will go up, all the orbitals, but still they remain degenerated. This is known as the barycenter. After further approach, they will split up into 2 levels, dxy, dyz and dxz, and dx square, y square and dz square. And again, for barycenter, it will be 3/5 of lower energy of total tetrahedral splitting and 2/5 of higher energy of barycenter for T2G, and Eg will be lower here. In tetrahedral coordination, the T orbital splitting is inverted and smaller as compared to the octahedral field splitting. For the same metal, the same metal ligands and the metal ligand distances. So here is the relation. Tetrahedral splitting energy will be 4/9 of octahedral splitting energy. It means if octahedral energy is, let's say, 900, tetrahedral will be only 400, less than half. This is the case when all metal atom ligands are same. Now we'll talk about the stability of coordination compounds. The stability of complex in solution refers to the degree of association between the two species involved in the state of equilibrium. Like here we have a metal atom, 4 ligands binds to it, make a Ml4. So this association constant will be equal to Ml4 divided by metal ligand to power 4. Here we are getting a metal combines to first ligand, getting a Ml complex. Its constant will be Ml divided by Ml, M into L. Second level, this Ml will combine with another ligand, give us Ml2. Its constant will be Ml2 divided by Ml into ligand. Same thing goes for the third stage. Metal bound to two ligands combined with the third ligand, giving us a Ml3. Ml3 having constant K3, Ml3 divided by Ml2 into ligand. Same goes to Ml4, fourth constant, Ml divided by Ml3 into ligand. What we will do, let's multiply all these constants. So what we are getting finally, Ml4 divided by M metal atom into ligands to power 4, which is nothing but total stability constant for this complex. So stability complexing of a 4 ligand is equal to multiplication of stability constants of individual 4 stages like K1, K2, K3 and K4. Overall reaction stability constant is the product of individual steps.